Right now in 2026, the Arctic has just recorded its lowest winter sea ice in 48 years of satellite measurements, for the second year running. At almost the exact same moment on the opposite end of the planet, Antarctica did something scientists say they did not expect at all. No winter has ever produced this little Arctic ice since satellites started watching in 1979. No ice sheet has swung from historic loss to what researchers are calling a historic turnaround this fast. It is not one polar crisis unfolding in 2026. It is two, moving in completely opposite directions, on opposite ends of the same planet at the same time. Stay with me, because the honest answer for why is still being argued over in the scientific literature. If you're new here, this channel breaks down real climate and earth science findings the moment the data comes in. So if that's useful to you, hit subscribe, it's free. Let us go back to the beginning. To understand why what's happening right now is so strange, you first need to understand what scientists expected the poles to do, because for decades, the expectation was reasonable and well supported by data. The Arctic is an ocean surrounded by land, covered by a floating skin of sea ice that grows through the dark winter and shrinks through the sunlit summer. Since satellite monitoring began in 1979, that skin has been thinning and shrinking decade after decade, and the physical reason is straightforward. As reflective white ice melts, it exposes darker ocean water underneath, and that darker water absorbs far more sunlight than ice ever did, which warms the water further, which melts more ice. Scientists call this the albedo feedback loop, and it is why the Arctic is now warming roughly 4 times faster than the planet as a whole. Nobody disputes this mechanism. It's basic radiative physics, confirmed by instruments for half a century. Antarctica, though, was always the strange exception, and for good reason. Unlike the Arctic, Antarctica is a continent, a landmass roughly 1.5 times the size of the United States, buried under an ice sheet that in places is nearly 3 miles thick, ringed by a belt of floating sea ice that behaves almost nothing like its northern counterpart. For decades after satellites began watching in 1979, Antarctic sea ice didn't shrink the way the Arctic's did. It held remarkably steady, and in 2014 it actually reached an all-time high extent. Scientists had reasonable explanations for this too. The Southern Ocean's winds and currents circulate differently. The continent's geography insulates it differently, and unlike the Arctic, Antarctica sits at the center of its own landmass rather than surrounded by warming continents pressing in from every side. For 35 years, this made Antarctica something climate scientists pointed to almost with relief, proof that the system wasn't uniformly collapsing everywhere at once. Scientists measure both of these systems the same basic way, using satellite microwave sensors that have been continuously operating since 1979, tracking extent, the total ocean area where at least 15% of the surface is covered by ice. That consistency is what makes this record so valuable. It's not 48 separate studies stitched together, it's one continuous instrument lineage, watching the same 2 regions, the same way, for nearly half a century. When a number from this record breaks a pattern that has held for decades, scientists take it seriously, because the measurement itself isn't in question, only the explanation for what's driving it. Then, starting in 2015, that resilience cracked. And in 2023, it didn't just crack, it fell off a cliff. Hold on to 2 numbers as we move forward, 1429 and 2.58. Both are measured in millions of square kilometers. One belongs to the Arctic's ice at its healthiest point of the year. The other belongs to Antarctica's ice at its most vulnerable. Both numbers, this year, told scientists something they were not prepared for. Here's the first number, and here's what it means in a way you can actually picture. On March 15, 2026, Arctic sea ice reached its winter maximum extent, the single largest area it covers all year, right before the spring thaw begins, at 1429 million square kilometers, or 5.52 million square miles, according to the National Snow and Ice Data Center at the University of Colorado Boulder. That number sits essentially tied with 2025's record of 1431 million square kilometers, meaning the Arctic has now produced its 2 weakest winters back-to-back in the entire 48-year satellite record. Translate that into something human scale. This year's maximum sits about 1.36 million square kilometers below the 1981 to 2010 average, an area of missing ice roughly twice the size of the state of Texas. Read that again. An area of ocean twice the size of Texas that used to freeze solid every winter, simply didn't in 2026. And this wasn't an isolated glitch in one corner of the Arctic. Climate scientist Zach Labe, who tracks the daily data closely, described the region as entering late winter in one of its weakest states of the entire satellite record, and pointed to an unusually wavy jet stream as part of the immediate cause, one that pushed cold Arctic air unusually far south into places like the western United States and southern Europe, while simultaneously dragging warmer air up into the Arctic itself to fill the gap left behind. The atmosphere, in other words, wasn't warming the Arctic evenly. It was actively trading places with it. Here's where it gets worse, because extent, the flat map view area covered by ice, was never the full story. Danish Meteorological Institute data from March 2026 showed that Arctic sea ice thickness across most regions has fallen below 2 meters, and total ice volume, which accounts for both area and thickness together, hit the lowest point ever recorded, roughly 15% lower than March 2024, just 2 years earlier. This is not a slow, gentle decline anymore. A study published in the Proceedings of the National Academy of Sciences in 2026 found something researchers had genuinely not anticipated. For a few years in the early 2020s, the long-term rate of Arctic winter decline had appeared to level off, weak enough that it no longer stood out statistically from ordinary year-to-year noise. Some scientists had begun cautiously wondering whether the decline was pausing. Then 2025 delivered the steepest single-year drop in the entire satellite record. 2026 extended it further, dragging the 20-year decline trend back to statistical significance. This is not chaos. This is a system that looked briefly stable and then proved, in the space of 2 winters, that it never actually was. Now hold that second number, 2.58, because this is where the story splits, in a direction almost nobody predicted. In 2023, Antarctic sea ice did something that had never happened in the satellite era. Its extent collapsed to a record low so far below anything previously observed that some researchers estimated the odds of it occurring naturally, by chance alone, at somewhere around 1 in 3.5 million. Not unlikely. Statistically almost impossible under the old assumptions. The years that followed didn't recover. 2024 and 2025 both stayed catastrophically low, with the 2025 minimum landing around 1.98 million square kilometers, roughly 30% below the historical average. By early 2026, the working assumption among most polar scientists was that Antarctica had permanently shifted into a new, unstable state, following the Arctic's decades-old pattern of decline. Then, on February 26, 2026, satellite data showed Antarctic sea ice reaching its annual summer minimum at 2.58 million square kilometers. Not a record low. Not even close to 1. It ranked as only the 16th lowest minimum in 48 years of measurements, and it spread the ice further around the continent than any of the 4 brutal summers that preceded it. Researchers at the National Snow and Ice Data Center called it exactly what it looked like on paper. A near-average year, arriving directly in the middle of what had looked like a runaway collapse. Sit with that for a second. The same system that fell off a cliff in 2023 essentially walked most of the way back up in 3 years. And even the scientists studying it weren't fully sure why. Here is where this stops being an abstract argument about satellite numbers and starts being something that reaches every coastline on Earth. Sea ice itself, floating and already displacing water, doesn't directly raise sea levels when it melts. But it does something arguably more dangerous. It acts as a reflective, insulating shield, keeping the ocean beneath it cold and keeping the far larger, land-based ice sheets behind it, protected from warm water and storms. When that shield weakens or disappears, it exposes the ice sheets sitting on solid ground. The ice whose melting genuinely does raise sea level, glacier by glacier, coastline by coastline. Greenland and Antarctica together hold enough frozen water to raise global sea levels by tens of meters if it all eventually entered the ocean. Nobody credible is suggesting that happens quickly. But every additional bit of thinning, every extra winter Arctic ice fails to fully reform. Every summer, Antarctic sea ice retreats farther than expected. Changes how much protection those land-based ice sheets actually have left. Coastal engineers in cities like Miami, Jakarta, and Rotterdam already build sea level projections directly off this data, planning flood barriers and drainage systems decades ahead based on exactly the kind of trend lines this year just complicated. That's the real stakes bridge here. This isn't a number that stays contained at the poles. It travels through ocean currents and planning documents alike into decisions being made about property, infrastructure, and where millions of people will be able to safely live a generation from now. Which is why scientists don't watch these numbers as a curiosity. They watch them as an early warning system for something that, once it starts moving at the ice sheet scale, cannot be stopped or reversed on any time scale that matters to a human life. The real detective story here isn't the Arctic. Its decline, while accelerating faster than expected, at least follows physics scientists have understood for decades. The real mystery is Antarctica, and reconstructing what actually happened between 2023 and 2026 took years of competing hypotheses, each one tested and partially discarded as new data arrived. When the 2023 collapse first hit, scientists scrambled for an explanation because nothing in the previous 4 decades of data had prepared them for a drop that extreme. The first hypothesis pointed to shifting wind patterns, the Southern Ocean's winds, rather than warming water, physically pushing ice away from the continent and preventing it from reforming. The second hypothesis pointed underneath the ice entirely. Warmer water from deeper ocean layers, previously kept isolated by stable stratification, finally breaking through to the surface and eating away at the ice from below rather than above, Both were plausible. Both had supporting evidence. Neither, on its own, fully explained the scale of what had happened. And for a research community that prides itself on being able to model this system decades into the future, that gap was uncomfortable. Some of the same scientists who had spent careers building the climate models used to advise governments on coastal planning were now watching the very system those models were built on do something the models themselves hadn't flagged as likely. That is not a small credibility problem in a field where the entire point is being trusted enough to guide multi-billion-dollar infrastructure decisions decades in advance. Through 2024 and 2025, as the low extents persisted rather than bouncing back, the ocean heat hypothesis gained ground, because researchers studying long-term Antarctic sea ice behavior noted something troubling. For decades, satellite data had shown the ocean surrounding Antarctica appearing to defy global warming almost entirely, holding its temperature while the rest of the planet heated up. That apparent resistance, some scientists began to suspect, wasn't the ocean actually staying cool. It was heat quietly accumulating in deeper layers, hidden beneath a stable cap of colder surface water, effectively banking warmth that hadn't yet been allowed to surface. If that theory held, the 2023 collapse wasn't a random anomaly. It was the moment the bank finally opened. And there was troubling supporting evidence even in 2026 itself. In the middle of the Antarctic winter this year, when a large stretch of West Antarctica, one of the coldest places on the entire planet, averaging around minus 34 degrees Celsius through the season, should have been frozen solid by every seasonal model, a significant area simply wasn't. Researchers pointed directly to that same hidden ocean heat, finally reaching the surface and interrupting the refreeze in the dead of winter, something no prior model had predicted could happen at all. But then came the 2026 summer rebound. Near-average ice spread wider than any of the previous 4 years, and it complicated the story rather than resolving it. If deep ocean heat had truly broken through and destabilized the system permanently, a sharp recovery like this shouldn't have been possible so soon. Researchers at the Cooperative Institute for Research in the Environmental Sciences pointed instead to a more immediate, more mundane cause for 2026 specifically, a shift in southern winds that, for this one season, happened to push surface ice outward from the continent rather than compressing it inward, spreading a similar volume of ice across a wider area. In other words, the wind hypothesis and the ocean heat hypothesis may both be partially right, operating on different timescales, tangled together in ways the current data still can't fully separate. Scientists resolved the immediate crisis of why does this keep failing to make sense, at least well enough to keep working. But the deeper question of which force is actually driving the long-term trend remains genuinely, actively unsettled. Here's what is happening right now, later in 2026, as both poles head into their next seasonal turn. In the Arctic, this record-tying winter maximum sets up what NSIDC scientists describe as a head start on the summer melt season. Thinner ice, less multi-year ice that survived a previous summer intact, and a pack increasingly dominated by young first-year ice that melts far more easily. Regionally, the damage isn't even. The Sea of Okhotsk, Baffin Bay, the Barents Sea, and the Kara Sea all recorded particularly weak ice cover this year, while a single pocket, the eastern Bering Sea near Alaska, actually saw slightly more ice than normal. A reminder that these trends, while overwhelmingly consistent in direction, are not uniform everywhere at once. Meanwhile, in Antarctica, researchers are treating the 2026 rebound with open caution rather than relief. The National Snow and Ice Data Center's own scientists have been explicit that this year's improvement does not prove the system has stabilized. It demonstrates only that Antarctic sea ice retains enough natural variability to bounce back sharply when short-term wind and ocean conditions briefly align in its favor. Separately, and on a completely different measurement scale, a study published in Science China Earth Sciences examined the Antarctic ice sheet itself. The grounded, 3-mile-thick mass sitting on the continent, not the floating sea ice around it, and found it had swung from losing about 142 gigatons of ice per year between 2011 and 2020 to gaining roughly 108 gigatons per year between 2021 and 2023, driven largely by unusually heavy snowfall in East Antarctica's Wilkes Land and Queen Mary Land regions. That gain, while real, briefly offset global sea level rise by only about 0.3 of a millimeter per year, a genuinely positive number, but a small one, riding on top of a far larger ongoing rise driven by every other melting ice mass on the planet. Adding another layer to this picture, NASA's Profire mission, a pair of shoebox-sized satellites launched, specifically to measure far-infrared heat escaping from both polar regions, has spent 2026 mapping, for the first time in this level of detail, exactly how much energy each pole radiates back to space compared to how much it absorbs. Mission scientists have described the goal plainly: Energy that was previously invisible to instruments is now visible, which mission leaders say should sharpen the same climate and weather models struggling to keep pace with exactly the kind of surprises both poles produced this year. There's a specific date on the calendar that turns all of this from an ongoing argument into an unavoidable checkpoint. On September 15th, 2026, the Arctic will reach its annual sea ice minimum, the single lowest point of ice coverage the entire year produces, measured every September without exception, since the satellite record began in 1979. Every scientist tracking this data already knows that data is coming, already knows roughly what range of outcomes is possible, and is already bracing for what a record low winter maximum typically sets up for the following summer. This is not a prediction dressed up as a certainty. It's a calendar fact. The measurement will happen, on schedule, whether the news is good or catastrophic, because it happens every single year, regardless of what anyone hopes for. What isn't locked in is the number itself. And given that this year's winter started from the thinnest, most fragile ice base ever measured, researchers are watching September 2026 with more unease than almost any previous minimum in the satellite era. Now, the honest part, because this is where a lot of coverage of this story oversimplifies what's actually known. Scientists do not currently agree, in any settled way, on how much of the Antarctic sea ice story is driven by short-term, reversible wind patterns versus a longer-term, harder-to-reverse ocean heat mechanism. And until more years of data accumulate, that question genuinely cannot be resolved from where we're standing right now. What most people are not seeing when this story gets simplified into Antarctica is fine now is that sea ice extent and the Antarctic ice sheet's actual mass are two completely different measurements, tracked by different instruments, responding to different physical processes. And a positive number in one does not mean the other has stopped losing ice overall. The 2021 to 2023 ice sheet mass gain was itself attributed to unusually heavy snowfall, which is, ironically, also a predicted consequence of a warmer, more moisture-laden atmosphere, meaning even the good news measurement may be evidence of the same underlying warming trend expressing itself in an unexpected direction. Scientists studying both records have been consistent on one point. A single good year, or even 3, does not overturn a 48-year trend, and nobody currently working with this data is calling either pole recovered. Zoom out from the specific numbers, and there's a bigger pattern worth sitting with. For most of the modern era of climate science, both poles were treated, understandably, as a single combined signal. Two barometers reading roughly the same pressure, moving in the same direction, confirming each other. What 2026 actually demonstrated is that they are two entirely different physical systems, governed by different geography, different ocean dynamics, and different feedback loops, capable of moving in opposite directions in the very same season without contradicting each other or the underlying reality of a warming planet. That's a genuinely uncomfortable finding for anyone hoping for a simple, single number to track. It means Antarctica bouncing back in one measurement doesn't buy the Arctic any time, and it means the Arctic's steady, predictable decline doesn't tell you anything reliable about what Antarctica will do next season. Each pole has to be watched, modeled, and understood almost as its own separate planet. This is also, quietly, a story about the limits of forecasting a genuinely chaotic system from a still short data record. 48 years sounds like a long time to a person, to a climate system that operates on ocean current cycles lasting decades, and ice sheet processes unfolding over centuries. 48 years is barely enough data to separate a real trend from noise, which is exactly why the same scientists who correctly predicted the Arctic's long-term decline were still caught off guard by both the speed of Antarctica's 2023 collapse and the speed of its partial 2026 recovery. Being right about the big picture and still being surprised by the details isn't a contradiction. It's what doing real science in real time on a system too large to fully control or fully observe actually looks like. Think about what that means for how this kind of finding gets communicated outside the research community. A single headline can only hold one direction at a time. Arctic ice hits record low, or Antarctic ice makes stunning comeback. And both of those headlines ran within weeks of each other in 2026, each one technically accurate, each one completely incomplete, without the other sitting next to it. The actual scientific picture was never a single story. It was two systems, tracked by the same instruments, reported by the same agencies, pulling in opposite directions for reasons that are still only partly understood, and reducing that to a single clean narrative in either direction was never going to be honest. There's an image from this year worth holding on to after the numbers fade. Satellite photographs taken on the same February day in 2026, one aimed at each end of the Earth. In the north, a thinning, retreating skin of ice barely holding its ground against a warming ocean, entering its most dangerous season with less protection than it has ever had. In the south, a wider, whiter ring than anyone expected to see again so soon, spreading defiantly back out across a sea that only 3 years earlier had abandoned it almost entirely. 2 photographs of the same planet, taken hours apart, telling what looks like 2 opposite stories, and both of them true, simultaneously, neither one canceling the other out. The Earth, it turns out, does not average itself into a single tidy number for the convenience of anyone trying to summarize it in a headline. So here's everything in one breath. The Arctic tied its own record for the lowest winter sea ice maximum ever measured in 2026 for the second consecutive year, with total ice volume the lowest on record and a 20-year decline trend that had briefly appeared to pause now confirmed as very real and ongoing. Antarctica, after collapsing to a statistically almost impossible record low in 2023 and staying catastrophically low through 2024 and 2025, unexpectedly rebounded to a near-average sea ice minimum in February 2026. Even as its underlying grounded ice sheet separately swung from historic loss to a multi-year mass gain driven by unusual snowfall. Scientists still don't agree on how much of Antarctica's turnaround comes from shifting winds versus deep ocean heat finally reaching the surface. And the Arctic is now heading into its September 2026 summer minimum from the weakest ice base it has ever had. 2 poles, 2 opposite trajectories, 1 unresolved planet. If you want to know what that September number actually turns out to be, and what it means for the season after this one, subscribe and turn notifications on, because I'll be covering it the moment NSIDC releases the data. Here's the question I want you to sit with. Does a genuine short-term rebound at one pole change how urgently you think about what's happening at the other? Or does one good measurement not move the needle for you at all? Tell me where you land in the comments. I read every single one.